Over the years, Android has evolved greatly in terms of its appearance and design language. It first started off as the bare necessities, no frills or niceties, it just got the job done. Although changes in appearance occurred, the underlying philosophy of design remained mostly stagnant. As phones became more capable and mobile technology became a bigger part of our lives, there needed to be a change, a way of humanizing Android more so than in the past. As we approached the middle of the 2010s, it was time for Android to embrace a truly intuitive interface. It was time to turn over a new leaf, a flat, seamless, colorful leaf, or material design. After watching this video, you should be able to have a clearer understanding of what material design is and the guidelines that are there to support it as a design system. Let's begin. When we think of design, there are usually visual rules in place to make a piece of work naturally attractive to the human eye. The rule of thirds, or the golden ratio, are examples. The rules of material design not only create a visually pleasing experience, but also provide consistency and functional cues as to what's going to happen next in the interface. The goal is to increase user immersion and enhance the user experience. So what exactly is material? Succinctly put, material is a UI design system defined by a set of properties in which any object within the system must adhere to. These object elements are loosely referred to as material. Think of it like a game engine, where all the physics, lighting, animation, textures, and etc. are bound by the properties of the game engine. The same goes for material design. There exists a 3D environment space where all the material elements function in ways that are constrained by the properties and guidelines set by Google. For example, all material elements have an X, Y, and Z dimension. All objects are 1 dp thick in the Z direction. The Z dimension is also used to show how high objects are in space, but we'll move on to this a little bit later. Looking closer at the material design language properties, there are 3 main types: physical properties, transformational properties, and properties of movement. These properties all combine to give a paper-like behavior that can change dynamically depending on its use. So before we start with material properties, let's take a look at some limitations. The limitations, according to Google's guidelines, are as follows. Materials are solid and cannot pass through each other. They also can't bend or fold. Okay, so let's take a look at material properties, beginning with the shadows. In UI design, traditionally, shadows exist to counteract blandness, but material design takes this further. Shadow graphics are one of the quickest ways of telling our brains where something sits in 3D space, or in other words, the relative distance between 2 objects. Here's an example. The square on the left has a height of 6 density independent pixels, or dp, on the Z-axis, and the shadow is drawn accordingly. The nature of the shadow changes depending on the height of the square. Shadows also help with understanding motion. On the right, we have a square that changes size. Notice how the shadow stays constant, indicating that the height is the same, so it must be the size itself that's changing. So let's see how movements are managed within material design. In the material design system, motion provides us with meaning. Material can be moved anywhere along the plane, but also can be raised vertically in the Z direction as mentioned earlier. When used in context of an actual application, a raise in the Z direction is usually a visual cue for user interaction. This is implemented using something called a dynamic elevation offset. A dynamic elevation offset is the destination position that a component moves towards relative to that component's resting state. For example, all components that lift on a press have the same elevation change relative to their resting state. Dynamic elevation offsets ensure that elevation changes are consistent across all component types. So in essence, it's a parameter to make sure that all upward movements of the same kind can be grouped together. There's an important aspect that has historically been somewhat of an afterthought for Google, and that is attention to detail in regards to animation and motion. This is no longer the case. Google now realizes that abrupt changes in speed or direction are jarring and draw unwanted attention. Material design is here to change this. An organic, asymmetric acceleration of an object can give an indication of weight. Lighter or smaller objects may move faster because they require less force, and on the other hand, heavier objects may need more time to speed up, behaving just the way you would expect them to in real life. Still on the topic of motion, let's talk about some transformation properties. Transitioning between two visual states should be clear, smooth, and effortless. A well-designed transition tells the user where to focus their attention. Google calls this motion package visual continuity. Google has 3 guidelines to consider when designing visual continuity. They are as follows. How should the user's attention be directed? What elements and motions support that goal? Transitions should be connected visually. Create visual connections between transition states through color and persistent elements. And finally, use movement with precision. Consider how moving a certain element adds clarity and delight to a transition. When it comes to making a transition, material design considers the order and timing of element movement. This conveys what content is most important by creating a path for the eye to follow. Google calls this hierarchical timing. According to Google, hierarchical timing should always use motion to direct the user's attention, but it should never allow element transitions to occur at the same moment, providing no indication of what's important. Okay, so let's move on. When transitioning elements are coordinated, it aids user understanding of the app. The paths that the element travels along should make sense and be as orderly as possible. Google terms this orderly transitioning as consistent choreography. To achieve consistent choreography in an app, Google suggests to do the following. Avoid conflicting movements or overlapping paths. Consider the depths at which the elements move and why. And this one's quite interesting. If all moving elements trace their paths on the screen, would it look beautiful and organized? Does it create a clear picture of where to look? The efforts that Google has gone through and the depth of their guidelines is quite impressive. Google has even made detailed guidelines on how to design icons, or how to write dialogue messages, or even guidelines for choosing the correct color scheme consistent with material design for your app. So, what's the conclusion here? What can we take away from all of this? Well, in summary, material design is mimicking reality. It brings a simple design system into a digital 3D space with well-defined parameters and guidelines. It intuitively conveys how an interface should work if it was made out of digital paper. The intuitiveness of the material design system aids in a fast understanding and recognition of UI behaviors with as little thinking by the user as possible. All in all, it's a great direction for Android, solidifying previously loosely tied ideas across the platform into a neat, uniform package. Okay, so that just about wraps up the video. If you want to learn more about material design, you can check out Google's official guidelines. If you want to see more videos of this style, you can head over to my channel, Cold Fusion. The link will be posted under the material design link in the description below. Thanks for watching, guys. Have a good one.